Okay. So, but does everything go in smoothly? Obviously not. We do have remainders. So suppose we have 7 divided by 3, and we try to divide this. What do we get? Well, what do we get? So what do we get? Well, let's actually do it. 7 divided by 3. Okay, 3 goes into 7 how many times? How many times does 3 go into 7? Not your question. How many times does 3 go into 7? Twice. Exactly. Twice. Now, 3 times 2, 6. We subtract that, and we get 7 minus 6, which is 1. Now, at this point, what we usually do is we add a decimal, add a 0, bring it down to 0, and we go, how many times does 3 go into 10? And we say 3 times, multiply, and we repeat our steps. Again, add another 0, and keep doing this. In the end, we have 2.3 bar, where the bar indicates that it goes on forever. However, right now, we are not caring about the decimal part or any of that. Right now, we are kind of right now, we're just doing the basic idea of division. So notice that when you divide, for this example, unlike 5 divides 20, for this example, you actually have something that's left over. Now, I'm sure everyone knows this, but I'm just going to restate it really quickly. This is your remainder. This is your quotient. The 2 is your quotient. How many times is this going to that? This is your divisor. And the 7 is your dividend. So now I can find what 7 is equal to. Well, I can rewrite all of this into something like this. So since 7 is being divided by 3, we see that we get some remainder. Well, I can say that 7 is the same thing as saying 3 times 2 plus 1. Right? I can say 7 is the same thing as saying 3 times 2 plus 1. This is a true statement. 3 times 2 is 6 plus 1, that gives me 7. So I can rewrite the division in terms of this. Does everyone see that? Any questions? Okay. So 7 is equal to 3 times 2 plus 1. Okay. Let's suppose we had another number. Let's suppose we had, I don't know, 231. Let's divide that by, let's say, 2. Well, 2 goes into 2 once. Multiply it. Bring down to 3. 2 goes into 3 once as well. There's this 2. Subtract 1. Bring down to 1. So 2 goes into 11 5 times. So this is 10. And we have a remainder of 1 again. Okay. Obviously, you already know that your remainder is not always going to be 1. But in the problems that obviously these two, it is in this scenario. If it helps you out, I can write 230. Let's keep it to 231. Well, I was going to say 233. How about that? 233. That way, you have a different remainder. Remainder is 3. Okay. So 233 is the same thing as saying 2 times 115 plus 3. So I can always rewrite it in that format. Any questions? Okay, so what I'm doing is I'm taking the quotient times the divisor. So the quotient times the divisor, and then adding the remainder. And in the end, that's going to give me the dividend. That's all I'm doing. So there are more. So are there ways? Are there ways where there are more than one answer? Like 2 times 116 plus 1. 2 times 116. That will be what? 12. 232 plus 1. So that's 233. Would you get 200? Wait, huh? Oh, because I changed this to a 5. That's right. Because I changed this to a 3. This should have been a 6 now. And this is 12. And this should be 1. So I still got a remainder of 1. I was trying to avoid that. Okay. Thank you. Okay. So 233 is equals to 2 times 116, not 115, 116 plus 1. Okay. Now, could have been 2 times 115 plus 3? Actually, it could have been. But we'll deal with that later on. So if you're doing it in this format, there should only be one type of answer. Because the way you guys were taught division, which is nothing wrong, but the way you were taught division is you want to make sure how many times does this go into it, or exactly, as close as it can be, or exactly, right? We never go below anything less than that. We always go like exact, or at least as close as we can. Nothing further from that. So this is what we have. Sweet. So in general, what I'm trying to say is that for a divisor, which we'll call A, for divisor, A can be rewritten using the quotients, the dividend, and the remainder. So divisor can also be rewritten as an equation using the quotient, dividend, and the remainder. And this is going to be A is equal to D times Q plus R, where R is less than D, but greater than or equal to 0. Also, A, B, let me give myself some space here, and A, B, A, D, Q, and R are some integer. Because that's literally what we're doing. We're taking a divisor and writing it as an equation involving the quotient, the dividend, and the remainder. And that's what I'm doing here. Where A is your divisor, D is your dividend, Q is obviously quotient, and R is your remainder. So I'll write that out. This is your divisor. This is your dividend. This is your quotient. Oops. And this is your remainder. This actually has a specific name. It is called the division algorithm. This is the division algorithm. Well, that's what we call it. I know you know algorithm as something different, but we call it the division algorithm. A is equal to D times Q plus R. Any questions? Yes, no? Okay. Now, again, like how we were saying here, So 116, so 2 goes into 233 116 times, right? 2 goes into 233 116 times. 3 goes into 7 2 times. So like what I was saying here is the way we were taught division, and yes, even I was taught division this way, was you pick a number that when you multiply with, takes you close to that number, the dividend, as close as possible, or maybe the exact same thing, right? That's what you do. So we can write that as this. So for the example, and let me keep it here next to it so you don't get confused. For 7 being divided by 3, if I'm just talking about trying to get a number that's close to it or exactly, what we're really doing is this. The floor function of 7 divided by 3. Now, the way we write this in the book is 7 divided by 3. It is simply the floor function, right? Because obviously you do get 2.333, blah, 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 blah. But if we only care about the quotient, then the quotient is the floor function. You're going to round down, which is 2. Or in a way of looking at it, you drop all the decimals. You want the number that's less than or equal to that number, 2.3323. And the number that's less than or equal to it is literally 2. So we're just interested in the quotient, then what we're really doing is just a floor function. Same idea here. If I do 233 div, which means we are only interested in the quotient, by 2, what we're doing is we want the floor function of 233 divided by 2, which is just 116. All right. If we would just want to denote, again, just the quotient. Any questions on this? Even if it goes evenly, 20 divided by 5, that's 4. Well, the floor function of 4 is still 4, because we want the number that's less than or equal to 4, and that number is 4. There's nothing that's less than or equal to 4. And it has to be 4. But what if we are interested in the remainder? We only want the remainder. Well, if we're only interested in the remainder, then we use a specific type of notation. 7, that's because I started with 7, that's why here. So I'm using this 7 divided by 3. 7 mod 3. 7 mod 3. And what is this going to give me? This is going to give me just a remainder, which is 1. So if I'm solely interested in the remainder, then I'm going to write it as 7 mod 3. And that equals to 1. So what if I'm just interested in the remainder of 233 divided by 2? Well, the remainder 233 mod 2 is equal to 1. Any questions on this? And this is only if I'm interested in the remainder. This will represent the remainder. Actually, let me check off the lines underneath so you don't think that's an additional notation. So that will represent the remainder. So let's suppose I gave you 10 mod 7. If I'm saying what's 10 mod 7 in this aspect, all I'm asking is what is the remainder of that? Well, the remainder, once you divide it, should be 3, right? Because if you take 10 divided by 7, 7 goes to 10 once, subtract, you get 3. So your remainder is 3. What is the remainder of 25 mod, let's say, 6? One, exactly. It's just simply 1. 6 goes into 25 4 times, as close as it can be. 25 minus 24 is 1. Sweet. So when you see that type of notation, keep in mind that that means that you're looking. Now, another way you will see this is in this format. Let me write it up here. 1 is congruent. Actually, let me write it here. 1 is congruent to 7 parentheses mod 3. 1 is congruent to 7 parentheses mod 3. So 1 is congruent to 7 modulo 3. So the way I'm saying this is 1 is congruent to 7 modulo 3. No, because the percentage one belongs only to a couple of programs. It doesn't belong to all of them, I think. If I'm correct about that. I think the percentage one only works on C and C++. Maybe Python. But I don't know if it works on other ones. Because that, yeah. I don't know about Python. I'm assuming I thought I saw it there, but I don't remember. So to answer your question, no, I would not be using a percentage one. Yeah, I don't even know what J5 is. Okay, now there's a big difference between this and this. Okay, there's a big difference between this and this, other than the fact that this is written on the left-hand side and this is written on the right-hand side. That doesn't really make much of a difference. That's not a big deal. Okay, all this is saying is it represents the remainder, and I can't believe I didn't finish writing remainder. Okay, it just represents the remainder of this. That's all this is saying. If I take this divided by that, if I take this divided by that, what is my remainder? That's all it's asking. It just represents the remainder. It represents R. This, on the other hand, represents a relationship on the set of integers. It represents a set of integers. Now, for example, 1 mod 3 well, let me actually give you the definition so you see what I'm talking about. So, definition. If A and B are integers and M is a positive integer, so I'm going to show you what I mean by relation. Then A is congruent to modulo to be modulo, sorry, to be modulo. If M divides the quantity A minus B, we use the notation A is congruent to B mod M. So notice I'm not saying the word equals because it's not an equal sign, okay? I don't know why I had to get up close to you guys about that, but it's not an equal sign. It has three things, okay? So when you're writing this, and you already know that I'm picky with notation, I'm very picky with notation. If you don't write the three little dashes, the three horizontal lines, I'm not thinking you mean modulo. I think you mean something else, okay? So make sure, I'm missing something here. Oops, modulo M. There it is. That's why it was looking all funky. Modulo M. Okay, so make sure you have pretty much those three horizontal lines. Okay, so make sure you have those three horizontal lines, because if you mean modulo, if you mean A is congruent to modulo B, so A is congruent to B modulo M, but you don't write this little three lines, you write an equal sign, I'm not going to assume that's mod, the modulo, which is this definition here. I'm assuming you're talking about just the remainder. Okay, so make sure I can tell easily between this and this. Don't go do something like that. Oh, that means equals, not congruent. No, that's just three little dots. That means something completely different. If you do this, that means something else. If you do this, that means 11. So make sure you take the time and just write out three horizontal lines. It takes time, but it doesn't take that long. But this is what I mean, that there's a big difference between this notation and this notation here. This notation only represents the remainder of whatever this is, just the remainder. This represents a relationship amongst the set of integers. Now, what is that relationship? Well, relationship is this. M divides the difference of A minus B. So M divides the difference of A minus B. Okay? So what does that mean? So if we have 7 mod 3, and I say, what is this congruent to? Then I'm stating this notation. I'm not saying what it's equal to. What is it congruent to? So what is this congruent to? Well, one is a possibility, because yes, I can do 1 minus 7, and that's still divisible by 3. I can also do 7 mod 3 is congruent to 0. Oh, actually, no, not 0, 7. That's what I meant, 7. 7 mod 3 is congruent to 7. So notice that these are the same things, but they're congruent to two different things, because this is true. So 7 mod 3 is congruent to 7. Why? Because I can do 7 minus 7, and that is divisible by 3, right? Because what's 7 minus 7? 0. Can 3 divide 0? Yes or no? Can 3 divide 0? Yeah, exactly. It's not a trick question. I'm not asking you guys a trick question. 3 can divide 0. So notice that these are set to two different things. They're congruent to two different things. Now, there are other ways on how to write modular. Whoa, not that. There are other ways on how to write modular, okay? There are other ways on how to write this. Now, you probably won't see it as much, and I'll try and avoid writing it like that. But sometimes when I was taught this, we wrote it like this. But I most likely will not write it like that. But if you see it, most likely that's how you will see it in some books. That way it looks cooler. It does. That's what it got stuck in my head. I remember when I was taught this, I was like, oh, that looks pretty weird because it's not something you're used to. So this means 7 is congruent to 1 mod 3 or 1. Wait, what do we do? I'm trying to remember. Hold on. 7. Oops, I have it backwards. This is supposed to be 1. This is supposed to be a 7. There it is. That makes sense. 1 is congruent to 7 mod 3. That's one way of writing. This one doesn't really matter which one's the 7 is because obviously you still get the same. 7 is congruent to 7 mod 3. But again, I'm going to avoid writing it like that because to avoid any confusion, your book doesn't really do that unless it's something very, very specific. Like I think they're doing addition, but you'll see that when you read the section. So I'm going to stick it to this, okay? Now, if I'm putting the parentheses, I'm telling you to do modulo. If I'm not writing the parentheses, and I'm writing it like this, that means I just want the remainder. Okay, that's the biggest difference between the notation in this book. If you see it like this, it means a remainder. If you see it like this, it means modulo. Okay, so determine for you guys, here's an example. Determined by the definition of modulo, 21 mod 4. So I want you to find that. I'll give you like a minute or two. Okay. Now if you're writing, I will probably write this in this type of notation. But see, that looks weird. Because there's nothing here. It just looks strange. All right, so determine 21 mod 4. Obviously, I want you to use the modulo. Let's see what you guys come up with. I'll give you like a minute or two. Again, make sure you use the definition. Make sure you use the definition of what modulo is. If you don't remember the definition, it's right here. Now, I'm expecting at least a couple of different answers. No, not everyone should have the exact same answer. And that's the interesting about mod. It really depends on how the mind thinks. So there will be a lot of different answers for this. Okay. So what are some answers for 21 mod 4? What is it congruent to? 1. What else? 5. Let's see. 5 minus 21, that's 16. Negative, obviously. Yeah, negative 16 is divided by 4. Awesome. Anyone has something else? Nine, let's see. 9 minus 21, that's 12, negative, but yep. It's divided by 4. How did you get 5 again? I don't follow that. So pretty much the idea is this. 20, so think of it this way. 4 will divide some answer minus 21. That's what you're thinking about. So what can you subtract from 21 such that it's divisible by 4? That's no way of thinking about it. So 5 minus 21 gives me 16. Yeah, it's negative, but 4 still divides a negative number. 13, yes, because if I do, that's going to be 8. It's negative, but it still works. Now, what I could do as well is negative 4. No, not negative 4, negative 3. And never said that it can be negative, right? Because negative 3 minus 21, that's negative 24. Negative 24 is divisible by 4. Nowhere in this definition does it say we have to have a positive integer, other than the modulo has to be positive, because that's literally what it says. M is a positive integer, but A and B can be any integers. And notice that integers can be both positive or negative. UHM. Oh, I think you just mean Is it like keep plus 4 unit until we get the largest number that's smaller than 21? I don't understand what you mean by keep plus 4 until we get the largest number that's smaller than 21. It doesn't have to be smaller than 21, because I could have said 47. Why 47? Well, 47 minus 21. Wait, not 47, 37. 37. Because 37 minus 21, I'm getting 16. And 16 is divisible by 4. So plus minus a multiplication of 4. Plus minus a multiplication of 4. It is like keep plus 4 until we get the largest number. I'm still really confused with what you're trying to say by that. 4. The normal one will be 1. What do you mean by the normal one? Oh, yeah. Okay, yeah. There's a pattern. Yeah, the pattern here is plus 4 minus 4, plus 4, plus 4, plus 4. This will be minus 4, but from this one. Yeah, I can see that. I see what you're saying now. If that's what you're implying. Now, if you mean by the normal one, meaning that that's what's remainder, if you're looking at it in terms of like this, then yes, this will be the actual remainder. However, these can also be remainders when you think about it. These can also be remainders. Well, how can they be remainders? Well, 21 divided by 4, right? And again, this goes to back how you were taught how to divide. We already know that should be 5, and that's we're going to get remainder 1. But we can also say this. 4 times 4, that's 16. I have a remainder of 5. So this is still a remainder, but in a different format. Obviously, it goes against what we believe on how to divide numbers, but it's not wrong either. This is still a remainder, isn't it? Same thing with 20, same thing with 9 here. I could say 4 times 3, this will be 12, and I get a remainder of 9. It's still a remainder. So this still represents a remainder, depending how we look at it. Does that make sense? Now, if we're looking at in terms of the definition, it is something that we take the difference of A and B, and then it's divisible by M. And that's how I usually think about mods, is 1 minus this, and then it's divisible by this. Or no way I thought about is, how much more do I need for this in order for it to be divided by 4? That's how I think of it. Okay, sweet. So we'll stop here for right now. Let's take a 5-10 minute break, and then we'll continue, okay? All right. Does anyone have any questions so far? Out of curiosity, is this the first time you guys seen modulo? I'm assuming not, since majority of you computer science majors. So, yeah, then you guys are gonna like chapter 4 for sure. Okay, let's move on. Oops. Now the next term. Term 4.1.5. Let m be a positive integer if a is congruent to b modulo m. And notice that if I say modulo, I'm talking about this type, the one with the congruence. And c is congruent to b modulo m. Then we have two conditions. Then a plus c is equal to b plus c modular m. Now, it bugs me, but I know what they're saying. This is the entire thing, okay? Goes in there. So imagine parentheses here. They don't write it in the book, and that's why it kind of bugs me. But they're talking about this entire thing. Okay? And you can also see it in a proof. You can also see it in a proof. What I mean by the proof is like if I quickly prove this, and obviously it's going to be a rough proof because I'm just quickly trying to show you this, why this is this and not, same thing with this. And then it's not this. If A is congruent to B mod M and C is congruent to B mod M, then M divides A minus B and M divides C minus B respectively. I know I didn't state it, where M is a positive integer and A, B, and C are nothing but integers. So by me saying M is a positive integer, that means there's no way M can be 0 because M0 is neither positive nor negative. It's neutral. So because M divides A minus B, then we're saying A minus B is equal to M times some T, and M times some S is equal to C minus B. And M divides this. So how can I get to B plus C? I could just add them. A minus B plus C minus B. That's going to equal to, oh, wait, I could just say this. A minus B is equal to M times T, and C minus B is equal to that. So then I can say oh, wait, A minus B plus C minus B, that is equal to A plus C minus 2B that right? A plus A minus B, so that'd be A plus C. So A plus C minus 2B. And then this is going to equal to oh wait, hold on. This is the same thing as saying MT plus MS. The same thing as saying T plus S. The same thing as saying A plus C minus B plus B. So the same thing as saying A plus C, if I view this as one thing, minus no, because if I'm trying to do that, I'm trying to get to B plus C. So what I'm trying to get to is B plus C minus A plus C. That's what I'm trying to get to. So that will give me B minus A. That's what I'm trying to show. So M divides C minus B. M divides B minus, oh, wow. This is B minus A. No, I had it right. A minus B, and that's C minus B. No, I had that right. Okay. A minus B, C minus B. A minus B is equal to M times T, and MS is equal to C minus B. I'm trying to show that B plus C, oops, not B plus C, A plus C minus B plus C, that's divisible by M. That's what I'm trying to show. A plus C. Oh, wait, we already know by theorem 4.1.1 I, which is this one here. If A divides B and A divides C, then A divides B plus C. Okay, so since M divides this and M divides this, then M divides A minus B plus C minus B. But this same thing is saying M divides A plus C minus B plus B. But I need a C in there. How can I get a C in there? M divides A minus B. Let me rewrite this. So M divides this. Actually, no. M divides A minus B, which means that we have A minus B equals M times S. M divides C minus B, which that means that C minus B is equal times M times T, where T and S are some integer. So on the way we're looking at it, we have A is equal to B plus MS, and C is equal to MT for B plus MT. If I add both of those, A plus C is equal to B plus MS plus B plus MT, right? So then that's going to equal to B plus B of MS plus MT Oh, oops, I have the thing wrong. That's why it wasn't working. This is supposed to be a D, which means this is supposed to be a D, which means that this is supposed to be a D. This is supposed to be a D, and A, B, C, and D are all integers. And this is a D, this is a D, this is a D. Oh, there it is. This is going to go B plus D, factor out the M, S plus T. Hence, M divides A minus, then we have A plus C minus B plus D. Let me write that nicer. A plus C minus the quantity B plus D, and this is equal to M times S plus T. There you go. Hence, M divides A plus C minus B plus D. Sorry about that. I completely botched the letters. That's why. So this should have been a D. I messed up, and I apologize for that. That's my fault. That's supposed to be a D, which means this is a D. Sorry about that. I just looked at my notes, and I wrote a B, and it's supposed to be a D. So where did MS come from? And MMT? Okay. They came from the fact that that's what it means to divide something. Remember the definition of this. So because M divides this, that means M times the multiple will equal to A minus C. A minus B, sorry. Same thing here. Since m divides c minus d, then m times t, m times something else, will equal the difference of c and d. And then all you have to do is just add them. Which in theory, I could just done theorem 4.11i and go straight to this. I didn't even have to do all of this part, not thinking about it. Can we get an x? I don't, an example. I was like, x. Okay. So let's suppose we have 7 is congruent to 1 mod 6. And let's say 5 is congruent to 1. Actually, no, let's say 3 is congruent to, let's say negative 3 is congruent to 3 mod 6. So by definition, actually, let's avoid negative so it can become a little bit simpler. Let's say, let's put a 3 here, and let's put 21. So by the theorem, so 7 plus 21 should be congruent to 1 plus 3 mod 6, according to this theorem. So what is that? 28 is congruent to 4 mod 6. So 28 minus 4 means 24. 24 is divisible by 6. So yes. So does that make sense? So that's what that theorem is saying. So that's one thing. The other thing that it states, well, I'm not going to prove this. I'm sure you guys can do this. Once you've written everything out correctly, I messed up with this. That should have been a D, not a B. A times C is congruent to B times D mod M. So that's what this theorem is saying. That as long as you have the same modulo, it doesn't matter what these are. If you add them or multiply them, they should still be congruent to mod M, modulo M, whatever that mod is. Assuming both of these statements are true. Obviously, one of these is false, then the other one's not going to be true. Good. That pretty much ends the section of 4.1. But any questions on that? Again, I'm sorry for taking too long on that proof. Just what I get for miswriting the definition. Yeah, it got pretty messy, and that's usually how proofs go. Like you get stuck, and then you reread what you have, and then yeah, you're like, oh, okay. But that's the complete proof. Now again, we're gonna make this proof a lot shorter because the other way that I was trying to do, but because I miswrote it, it didn't come out either, is by theorem 4.1.1i, I could have just said m divides a minus b plus c minus d, and then manipulated this to look like this. And then it would have skipped all of this. It would have skipped all of that. And that's actually what I was trying to do. But the problem is I had a B here and it should have been a D. So that was my issue. Okay, now section 4.2. We may not finish all of this, but it's going to look familiar for a lot of you. Theorem 4.2.1. Let B be any integer. and b is greater than 1. Then, if n is any positive integer, can you scroll up real quick? This part? Okay, sweet. Okay, then if n is any positive integer, it can be expressed in the form n is equal to a sub k b raised to the k plus a sub k minus 1 b raised to the k minus 1 plus blah, 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 plus a sub 2 b squared plus a sub 1 b to the first power plus a naught times, well, we don't write this last part because we just don't, b naught. Now, I'm sure most of you may know the short version of this. This can also be expressed as, and I'll write it in brackets. And then it'll be like, oh, I know what this is. Parenthetical, so within the parentheses, a sub k minus 1, a sub k minus 2, blah, 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 a sub 2, a sub 1, a naught, sub b. Where k is a non-negative, meaning it could be any number that's positive and 0, a sub naughts, a sub 1, all the way a sub k are non-negative integers less than b. Again, they could be zeros. And a sub k cannot equal to 0. Well, right there. So that's the thing we're starting off with. Okay. Now, what does this represent? Well, this is, or pretty much this entire thing, so I shouldn't just focus on that. This entire thing is the base B expansion of n. That's what this is. The base expansion of n. So in other words, we can change bases. That's what we're doing. So for example, suppose we have 381 and we want to change it to base 10. Well, we go by the definition. So notice I'm writing it in this notation. By the definition, we do this. This is equal to 3 times 10 to the second plus 8 times 10 to the first plus 1 times 10 to the 0 power. Well, actually, we don't need times 10 to the 0 power because that's just 1. What is that? That's just 300 plus 81 plus 1. Oops, not 81, plus 80. So this is just 381. And yeah, that makes sense. I kind of expected that. right? That does make sense. Like 381 changed to base 10. Well, yeah, it should have been 381. There should have been no difference. Any questions so far? But let's not do base 10. Let's do a different base. What if we want 381 to change to base 9? What if we're interested in base 9? Okay, what if we're interested in that one? Well, that's 3 times 9 squared plus 8 times 9 to the first plus 1. Now, if you're still having trouble, what do you mean by bases? Well, the way we count is base 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then repeats itself. 0, which is 10, right? Then we have 11, 12, 13, 14, 15, 16, 17, 18, 19, another 10, so now 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, another 10, so reset itself, 30. That's what it means. Computers are base 2, which are nothing but zeros and ones. So 1, 0, reset itself. 1, 0, 1, 1, reset itself. 1, 0, 0, 1, 0, 1, and so on and so on. Right? So computers are base 2, of my understanding. They're binary. If you're studying Babylonians, they're base 60. They're base 60. They counted in 60, in groups of 60. If you're going by the Mayans, they were base 20. Base 20. So if you wrote, so they counted by 20s. Okay, so now this is 3 times 81 plus, what is that, 72 plus 1. That's 243 plus 72 plus 1. Now, what does that equal? Oh, that's going to be 5, 11, 315 plus 1, 316. So 381 in base 9 is 316. Any questions on that? Any questions? You guys are good? Okay. So what if I wanted it in base 2 then? 381, but in base 2. Well, that's going to be 3 times 2 to the third plus 8 times 9 to the first plus 1. Actually, not to the third, to the squared. Okay. So that's 3 times 4 plus 72 plus 1. That equals to 12. Oops, not 72. That's supposed to be a 2. So that's 16. Okay. So that's 12 plus 16 plus 1. So what is that? 28. So 29. Good. Any questions? Any questions? So that's what this theorem is saying. And again, oh wait, you know what? This one I messed up. This shouldn't be in 2. There should be non-negative integers less than b. Oops. So in other words, I couldn't have done this at all. Now what I could have done is 1, 0, 1. So what is that? 1 times, that's squared, plus 0 times 2 plus 1. So that's 2, no, that's 4. 4 plus 0 plus 1, which is just simply 5. Sure, that makes more sense now to some of you guys. Good. Any questions on this? Any questions? So again, all of these have to be non-negative integers less than b. Less than b. Now, what's saying by a sub k can't be 0, it means the leading one cannot be 0. So this one cannot be 0. That's what it's saying here. Okay. No questions? I'm just trying to make sure. Or some of you guys are really happy with this, I'm sure. Yes, no? All right, I'm getting nothing, so I'm assuming. Okay, now, that's how you change the basis. That's what we did here, that's what we did here, and that's what we did here. Well, what if I want to go backwards? What if I want to go backwards? How do I go backwards? Well, the idea that we did here, all we did was took each one of these integers and multiply them by the base. So base 9 to second, then base 9 to the first. Technically here, this is base 9 to the 0 power. Okay, so what we did is we multiply each integer by a specific multiple of that base. So if we want to go backwards, or we want to go back to what we originally have, like I want to change back 316 to 389 to 381. Can I do that? Well, the answer is yes, by doing the opposite, which instead of multiplication, we do division. So suppose we have 316 and we want to go back. Okay, so I want to show that this goes back to 381. So all we have to do is divide that by 9. So what's 316 divided by 9? Obviously, you're going to need a calculator. It's not going to go in evenly, and we don't want it to go in evenly. If it goes in evenly, that'll be great. But what I'm trying to say is we don't want to use a calculator to the point where we write out the decimals. What you want to write it as is using the division algorithm. So this is 35 times 1. So far, so good. We're not done yet. What do we do next? Well, you take the quotient, which is 35, and you divide it by 9 again. What do we get? We get 3 times 9 plus 1. Because if you do 9 times 3, that's 27, right? And 27 is the thing that's closest to 35. But you still get a remainder of 1. Wait, no, you don't get a remainder of 1. You get a remainder of 8. Right? Because 35 minus 27 is 8. We're still not finished. We take 3 again. We take this 3 and we divide it by 9. Now, what's 3 divided by 9? Well, the thing that comes closest is 0. 0 times 9, and we get a remainder of 3. Right? Because 9 does not go into 3. 9 goes into 3 0 times. So we have a remainder of 3. And at this point, we stop because we have this 0. That's when we stop. When we see the 0, stop. So notice that, look at these integers, the remainders, it is 1, 8, 3. So that's 381 base 9. So that's 316. Any questions on this? Any questions? Yes? No? Well, another one that we did was this one. 101 base 2 became 5. So what if we want to do that one? Or what if we want to get back to 101? Can we do that? Well, let's find out. 101 base 2 was equal to 5. Let's say I want to go backwards. So I'm going to take the 5. I'm going to divide it by 2. Okay. Well, 5 divided by 2. Well, I'm going to multiply the 2 by some 2. And I'm going to add 1. Right? Because I will get a remainder 1. And you get this 2. You divide it by 2. So it's going to be 2 times 1 plus, well, 0. There's no remainder. And it's best for you to put that 0 there because if you don't, you might forget about it. So make sure you actually put it. Then when I finish, you get the 1 divided by 2. How many does, so that will be 0 times 2, but you get a remainder of 1. No, you get a remainder of, no, yeah, you get a remainder of 1. There's 2, how many times does 2 go into 1? And notice that we get back 1, 0, 1 base 2. Any questions so far? Pretty straightforward. So what if then that means wait, then by that theory or by that logic, what if I want to convert it to some other base? What if I want to change it to some other base? For example, 381 base 9. What if I want to change it to another base? What if I want to change it to base 8, octal? Well, we already know that 381 base 9 is equal to 316. So if I want to change into an octal base, meaning 8, base 8, all I have to do is take 316 and divide it by 8. All right, that's all I have to do. So what's 316 divided by 8? Well, how many times does 8 go into 316 or close enough? Well, I don't know that. So 316 divided by 8. 8 goes into 31 3 times. That's 24. So then that's going to be what? 76. Right? So 9. So that'd be 72 with a remainder of 4. So we have 39 times 8 plus 4. Then we get, we're not done yet because we eventually want to get to 0 times 8. That's what we eventually want to get to. Because again, the last examples too, when we got to 0, we stopped. So 39 divided by 8. Okay, so 39 divided by 8. How many times does 8 go into 39 or close enough? Well, that will be, what is that? 4. So that's 32. And we get not 6, 7. We get a remainder of 7. 4 times 8 plus 7. Obviously, we're not done. We get 4 divided by 8. How many times does 8 go into 4? Or 0 times. But then we have a remainder of 4. So notice that we got 0 again. So we're going to stop. So my answer is 381 base 9 is the same as saying 474 base 8. Does that make sense? Any questions on this? Any questions? Does this look familiar to some? I'm assuming this looks familiar to some of you. Not everyone, but maybe just some of you. Okay. Right. Now, in your book, they will be talking about the main three types, well, main four types of notations that the computer uses. We're going to talk about binary. Binary is just zeros and ones. Octal, which is 0, 1, 2, 3, 4, 5, 6, and 7. Then decimal, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the one that we know, base 10. That's what it means by decimal. Then we have hexadecimal. Now, hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then A, B, C, D, E, F. But for just those who don't know, A is equal to 10, B is equal to 11, C is equal to 12, D is equal to 13, E is equal to 14, F is equal to 15. So pretty much hexadecimal is base 16. I really don't know why it's A, B, C, D, and F. I really don't know why it's A, B, C, D, and F. But that is the ones that you will see as well within this section. Those four common bases: hexadecimal, decimal, octal, and binary. These are the ones most common in computer science. And yes, you can change from hexadecimal to whatever other base you want and vice versa. Just keep in mind that A, B, C, D, and F all have a specific integer. A is 10, B is 11, C is 12, 13 is D, E is 14, and F is 15. And that's what this section's about, the conversions of bases going back and forth. Being able to change from the binary to octal, octal to binary, octal to hexadecimal, and vice versa. Any questions? So again, all what this is doing is this is a number that's in base 2, so we're going to change it, and it's going to be 5. That represents 5. So if this is 381 base 10, and we change it, it's 381. This number here is 381 in base 9, but we change it, we know that that number is 316. Okay? Does that make sense? Any questions on this? You guys are good? Okay. So right here, we'll stop because we are running out of time. And also, I wanted your opinions on the exam. What did you guys think of the exam? I'm just curious. I still got to put the exam instructions or the quiz instructions. Okay. Yeah, I was more concerned about like if it was too many questions because I know the time and I know some of these problems take a while to do. Yeah, I supplied the table because I said that if I was going to give you something like this, I was going to supply the table. So I was trying to keep my word on that. What part of the instructions confused you? I'm just curious. Because then I can like clarify it for the next exam better. Like, are you talking about a particular problem? Oh, okay, yeah, that's something different then. I'm trying to see. Number one, problems 3 and 1. Statements in column 3 and 1. What statements? So you're talking about you're talking about the prompts. So number 1, oops, wrong class. You guys are not in 151. You guys are on 171. Let me look at it so I can understand what you're talking about. Oh, well, for those, for number 1, what I want is some work, yes, because I wouldn't expect anyone to know that on top of their head. Like, I will need to at least see some work, like the logarithms. Like, you should be able to combine those. Eventually, you realize how I can combine, simplify all of this, and come out to the fact that it may or may not be 2. Same thing with the part B. You don't know if this is true or not unless you figure it out. So yes, there needed to be some work shown for that one. Number 3, but in 3, you just had to say what that statement, like, you had to figure out if it was valid or not. So if it wasn't valid, give reasons to why. So you will give like a counter example, assuming it wasn't valid. If it is valid, then you say, yeah, this is valid, and here's the reason why. And that's why I gave you the table. So you can like, oh, okay, you know what? Maybe because of this reason, it's valid. Does that answer your question? Yeah. So for number 1, which is the one with the logs and system of equations, yes, you should have shown some work, because I wouldn't expect anyone to do that on top of their head. And also because it says this should be done without a calculator. So I was expecting no one was using a calculator whatsoever. Cool. Oh yeah, be careful. That's why make sure you have. I actually like number 2. Number 2, that was a good question in my opinion. I was like, oh, that's an interesting question. So, yeah, for that one, that was an interesting question. All right, sweet. So it looks like the exam was good enough in terms of time-wise, how many questions. Because I know I'm doing it online is a little bit different. Obviously, if it was in person, then I can see it. Like, oh, okay, everyone finished, someone didn't finish. So, all right, cool. All right, if you have any questions, let me know. Other than that, see me during the office hours. Again, I'm going to try and update the grade so you can see it on Canvas. Just keep in mind that your grade on Canvas it will be a little bit different because sometimes I can't control those weights. But you can always see me and we can talk about your grade. And again, you have the rubric within the syllabus, the 20%, 30%, all of that. If you want to calculate what your grade is, and what you can use is pretty much the averages of your quizzes, discussions, and exams, which obviously you can't use the exam yet. Sweet. All right. Other than that, I'll see you guys Thursday.